We now look at the case where we have repeated real roots in the denominator of f of s. You'll recall from a college algebra class where you learned how to do partial fraction expansion that this type of situation where you've got a repeated root, in this case the s plus 5 factor is present with a multiplicity of 3, we can rewrite this in a partial fraction expansion as k1 over s plus k2 over s plus 5 cubed. But we also need to add in two more terms, k3 over s plus 5 squared plus k4 over s plus 5 to the first power. We can evaluate k1 and k2 in exactly the same way that we have in the past. So to get k1, we'll multiply both sides of this equation by s and then evaluate it at s equals 0. So f of s evaluated at s equals 0, on the left-hand side we'll have 100 times 25 over 0 plus 5 is 5 cubed. And then on the right side we have, of course, you multiply everything over here by s, and you're going to have k1 by itself, and each of these terms will have s's that when evaluated at s equals 0, they go away. And so we get then that k1 is equal to that, or k1 equals 20. Pretty straightforward. We can get k2 in a similar way, only this time we're going to multiply both sides of the equation by s plus 5 to the third power f of s, and evaluate that at s equals minus 5. On the left-hand side, we have 100 times s plus 25 over s, which is going to be evaluated at s equals minus 5. On the right-hand side, we're going to have on the right-hand side, we'll have k1 times s plus 5 cubed over s plus, now when we multiply this term here by s plus 5 cubed, the s plus 5 cubed terms cancel, and we're left simply with k2, plus here we'll have k3 times s plus 5, and then here we'll have plus k4 times s plus 5 quantity squared. And of course, all this side over here is also going to have to be evaluated at s equals minus 5. As you can see, when we do this, this term, and this term all go to 0. And we're left simply with k2 on this side here. And over here on this side, you evaluate this at minus 5, and we have 100 times minus 5 plus 25 divided by minus 5, and that equals minus 400. And we have k2, pretty straightforward. Now, getting k3 and k4 is a little more tricky. Our trick to this is going to be that we'll go back to this form right here, the s plus 5 cubed times f of s, and before we evaluate it at s equals minus 5, the trick is to differentiate both sides of this equation before evaluating it at s equals minus 5. So right here is s plus 5 cubed times f of s. We see that the quotient rule is going to come into play because we have s's both in the numerator and the denominator. So let's just remind ourselves up here that the derivative of u over v is equal to v du minus u dv over v squared. So when we take the derivative of this term right here, we've got v, which is s. So d by ds of s plus 5 cubed f of s. The left-hand side is going to be s times 100. So v times the derivative of the numerator derivative is just 100, minus u dv, which is, well, u is 100 times s plus 25, and dv, well, v is just s, so the derivative of s is just 1, and all of that will be then divided by v squared, or s squared. That's what we get on the left-hand side. The right-hand side starts to get a little bit messy. We're going to see, first of all, that when we take the derivative of k2, the constant, that's going to go away. But first we need to take the derivative of this first term, which is going to be the denominator s times 3 times k1 times s plus 5 squared minus k1 times s plus 5 cubed times the derivative of s, which is just 1. So we can close that off, all divided by s squared. Let's see, I think I got the parentheses in the wrong place. This is v times du minus u times dv. Well, there's u, the numerator. Numerator is just k1 times s plus 5 cubed times the derivative of s, which is 1. Okay, there, that's right. That's the derivative of the first term. We have then plus the derivative of k2, which is 0. Now, the derivative of this term right here, k3 times s plus 5 to the first power, that's just going to be plus k3. And then finally, the derivative of this last term, we've got k4 times s plus 5 quantity squared. The derivative of that, let me just write it down here, is going to be plus 2 times k4 times s plus 5 to the first power. Okay, so now we've differentiated the left side and the right side, all right here. We now evaluate it at s equals minus 5. So evaluate at s equals minus 5. On the left-hand side, we get, let's see, minus 5 times 100 minus 100 times minus 5 plus 25 divided by minus 5 quantity squared. Over here on the right side, all of this, each of these has an s plus 5 term, which when evaluated at s equals minus 5, those drop out. So this term goes to 0. This term is already 0. This term similarly goes to 0 when you have s equals minus 5, and so we're left with just k3 on this side, and you do the math, and you get that k3 is equal to negative 100. So, very quick review. We take and multiply both sides of f of s by the s plus 5 quantity cubed term. But before evaluating it at s equals minus 5, we take the derivative of both sides and then evaluate it at s equals minus 5 to give us this k3 term. So, getting k4 now becomes a little bit tricky. K3 was tricky because we differentiated one time before evaluating. To get k4, we're going to differentiate s plus 5 cubed times f of s 2 times before we evaluate. So I've gone through and just kind of made a table here of the work that we've done up to this point. Here's the s plus 5 quantity cubed times f of s. The left side of it is that. The right side of it is that. So that term where we had k1 over s, it's k1 over s times s plus 5 quantity cubed. It was plus k2 over s plus 5 quantity cubed, which when multiplied by s plus 5 quantity cubed, the s plus 5 quantity cubed terms canceled, leaving us just k2. Over here we had an s plus 5 quantity squared in the denominator, which when multiplied by s plus 5 quantity cubes leaves us an s plus 5 in the numerator, and similarly there. Now, we already did, and so I'm just rewriting here. The derivative on the left side was this. The derivative on the right side was this. Now, to get k3, we simply evaluated both sides of this at s equals minus 5, and we were able to solve for k3. We already did that. To get k4, we'll take this first derivative, and before we evaluate it at s equals minus 5, we're going to differentiate it one more time. To do that, simplify this term here so that the first derivative on the left side, first derivative simplifies to this. This doesn't really simplify very much, so we're going to just have to grind through the derivative of that. But over here, the second derivative is then v times the derivative of the numerator, but since the numerator is a pure constant, the derivative of the numerator is 0, minus the numerator, which is negative 2500, times the derivative of the denominator, which is 2s, all divided by the denominator squared. Well, the denominator was s squared, so s squared squared is s to the fourth. Now, over here, this gets to be actually quite a bit more grimy. Once again, it's the derivative, or it's the denominator, s squared, times the derivative of the numerator. The derivative of the numerator is a little bit tricky because we've got the product rule coming into play. We have s times k1 times this minus that for our numerator. So we have s squared, the denominator, times the derivative of the numerator. Well, the derivative of the numerator is 2 times s times k1 times s plus 5 to the first power, plus, so that's we're doing the product rule here, so that's the derivative of the first, or the first times the derivative of the second, and then we have plus k1 times s plus 5 squared times the derivative of s, which is just 1. These two terms then are the result of the product rule operating on this, minus the derivative of this, which is minus 3 times k1 times s plus 5 to the second power. This then is the derivative of the numerator times the denominator. We now need to take the derivative of the denominator and multiply it by the numerator. So the derivative of s squared is 2s, and of course it's minus u dv. So it's minus, there's the dv. Here is the numerator of that term there. All divided by the denominator squared. So this whole thing right here is just the derivative of this term. We have then, continuing on down here, we have the derivative of 0, of course, is 0. The derivative of k3, the constant, is 0. And here, the derivative of this with respect to s is just 2 times k4. So, you evaluate the left-hand side of the second derivative, and we got minus 40. Over here, evaluating all this at s equals minus 5. Note that all of these terms have s plus 5 terms multiplying them, except the term involving k4, which we have 2 times k4 here. So we get 2k4 equals minus 40, or k4 equals minus 20. With the values of k1 through k4, we can now write f of s in its expanded fraction form, which is 20 over s plus minus 400 over s plus 5 quantity cubed plus a minus 100 over s plus 5 squared minus, or plus, a minus 20 over s plus 5. That's an s right there. S plus 5. And now we need to simply transform each of these back into the time domain using our Laplace transform tables. We know that this first term, with it just 20 over s, that's going to go to, let's write this, that f of t then is equal to 20 times u of t, but all of these are going to have u of t terms in it. So let's just write the u of t term here in just a second. Factor it out and write it for all of them. Now, we have an s plus 5 quantity cubed in the denominator. From a table of Laplace transforms, we find that in the s domain, something of the form n factorial over s plus a raised to the n plus 1 power corresponds to a time domain function of the same constant multiplier out here, t to the n e to the minus at. In other words, when we have higher ordered powers, or let's see, how should you say this? Roots with multiplicities greater than 1 in the frequency domain, we end up multiplying by a t to the nth term. We have this t to the nth term multiplying the exponential term. So 1 over s plus a simply goes to e to the minus at. 1 over s plus a to the n minus 1 has some additional complexity to it. So let's just look at this. We have our highest power is s plus 5 cubed. So looking here, the power of the denominator is 3. The power here in the denominator is n plus 1. So this tells us then that this is really s plus 5 to the 2 plus 1, or that n equals 1 here. And we can rewrite this term, the negative 400 over s plus 5 cubed. We're going to pull out this, since n is equal to, I said n equals 1, n equals 2 here. Sorry about that, n equals 2. We need to get it into this form where we have an n factorial or a 2 factorial. Here I have a constant of minus 400, so I'm going to write that as minus 200 times n factorial, which is 2 factorial, over s plus 5 to the 2 plus 1 term. In this form, we now have a k value of a negative 200. We have the n factorial, which is 2 factorial, or just 2, over that. This here then goes to, and thus this term here will transform or correspond back in the time domain as, let's see, negative 200, so plus a negative 200 t to the n is 2, so t squared e to the minus 5t. Similarly, this term here has an s plus 5 to the second power. Using this same kind of a situation, we have then n equals 1, 1 factorial is 1, and so for this second term, we have then the k is negative 100 times 1 factorial, let's see here, divided by s plus a to the 1 plus 1 term. Of course, a here is 5. So now, this third term, in this form, our k value is a minus 100. Our n value is 1. So we'll have then, corresponding to this term here, we're going to have plus a negative 100t e to the minus 5t. And then finally, we have this last term, which is just has s plus 5 to the first power. And that, of course, goes to a, we'll write it this way, plus a minus 20e to the minus 5t. And I didn't leave myself enough room, but there's a u of t multiplying that whole thing. Let's just look at this a little bit more closely. what we see is that because we had an s plus 5 to the third power and second power and first power, we ended up with a multiplier of t squared, t to the first power, and t to the 0th power. This is reminiscent of the variation of parameters that you saw. For those of you who have had the differential equations class, is reminiscent of the variation parameters method that we came up with to distinguish particular solutions for situations where we had only a single value, a single root. In this case, the single root is s equals 5, but it shows up in a multiplicity of 3. That multiplicity of 3 then, just to close it and finish it up, required then, or resulted in, these multipliers of t squared and t to the first power.